Let's take a look at the following question. Two chemicals, A and B, are combined to form chemical C. Initially, there are 81 grams of chemical A present and 43 grams of chemical B. Suppose it takes 5 grams of chemical A for every 7 grams of chemical B to form chemical C. And further, suppose the reaction begins with 0 grams of chemical C, and after 7 minutes, the reaction has produced 10 grams of chemical C. We've got 4 parts here, A, B, C, and D. The first question, part A, write a differential equation to model the reaction. Let x of t represent the amount of chemical C present in grams at time t measured in minutes. Okay, there is a lot going on in this question, and there are multiple parts, so let's begin with part 1. Again, two chemicals A and B are combined to form a third chemical C, and it says here initially there are 81 grams of A present and 43 grams of B present, and the rate at which that chemical C is produced is based on what a model that we'll use here that's called the law of mass action, which is to say that the rate of growth of that chemical C, the rate of increase in chemical C, it's proportional to the amount of the other chemicals that remain. And so we'll start off building a mathematical model for the rate of reaction where chemical C, represented by X, grows proportional to the amount of the other two chemicals that remain. So there'll be a constant of proportionality and then two factors that represent the amounts of each of the other chemicals that remain. So this could represent chemical A, and this could represent the amount of chemical B that remains. So what was initially the amount for chemical A? It was 81 grams, and then it's going to decrease over the time of the reaction. And what was the initial amount for B? That was 43 grams, and that will also decrease. Now, what rate is it decreasing? So first of all, I can see that the 81 grams is here and the 43 grams is here, but what I need to focus on now is the rate at which these other chemicals A and B decrease. So it's given here. For every 5 grams of A, it takes 7 grams of B all together to form chemical C. So essentially, all of A and B are combining in to make C, and so we could look at this as saying we're going to take 5 from A and 7 from B and make 12 grams of C. And so what we'll do is we'll add together the 5 and the 7 and make 12, and use that to say there's the fraction 5 over 12 times the amount that I currently have of chemical A, which is measured in X, right? So for every 12 grams that I make of chemical C measured by the variable X, I'm going to take away 5 from A, and for every 12 that I make of chemical C measured by the variable X, I'm going to take away 7 from B. So imagine for a moment that you had 12 here and 12 here. Then you would take away 5 and 7 from each of these. So that's kind of the rate at which we know that A will decrease and B will decrease. For every 12 units of chemical C, we'll take 5 from here and 7 from there. And that's why we have that expression there. It's going to be this one plus this one in the denominator in each of those. And just to repeat, this K is a constant of proportionality. Okay, so now this is good progress. This is the first part, part 1. That checks. That's what the computer was looking for, as you can see there at the bottom of the screen. Let's go to part B. Part B asks us to now solve this differential equation, right? So we have dx dt is a constant 81 minus 5 over 12x and 43 minus 7 over 12x. And actually, we can't get a particular solution yet because we don't know the constant proportionality And that's given by the amount of the chemical present after a certain amount of time. So let's look back at the original question. There is more information here given. It begins with 0 grams of chemical C, and after 7 minutes we have 10 grams. So we have initial conditions. So let's include that now. X at time 0 is 0, and X at time 7 is equal to 10. 10 grams at 7 minutes, and 0 grams initially for chemical C. So this is now an initial value problem for which we can actually solve for X and find the value of K. That constant proportionality is like the proportionality, the rate at which chemical C is produced over time. If we're going to solve for X as a function of T, we're going to need to be able to get that constant proportionality, which comes from the rate at which the reaction occurs, which is given by those initial conditions. In fact, boundary conditions, because we know the X at time 7 is 10, and that's now enough to get that constant proportionality. Okay, so now in order to solve this, those factors there, with those fractions like 5 over 12 and 7 over 12, combined with these other given values, so arbitrary, it's difficult actually to go through the algebra with these fractions. It's actually easier to solve this problem if we just do it once and for all with arbitrary values that are variables and see how the solution comes out in general, and then in that sort of general solution we can plug in the given values that we have. So I'd like to approach the problem that way. I think it's also a valid, important way of seeing how this could work out. So what I'm trying to say is that I want to solve not that particular one there, but I want to solve in general a differential equation that has this form. Let's say you have A minus B times X and C minus D times X. And let's say that at time 0, you have 0, but let's say at some arbitrary future time, you have some arbitrary future amount. So at time 0, we'll keep it 0, but at time 1, so at one point later in time, we have some x1 value that represents the amount of chemical C at one particular point later. Right? So I'm going to solve this general problem, and then once we've done that, we can go back and plug in the numbers. So in this instance, of course, this is 81. That B is, I'm going to use just 5 over 12 later for B because I already have the minus in the equation, right? And so my C value, that's going to be 43, and the D value in this specific one. Of course, the point is that in my open math, you're going to have these algorithmically generated questions. The numbers are going to change. And so we want to track that. Here, the time is 7, and this is 10. Right? So why don't we just go about solving this in general for just values A, B, C, and D, T1 and X1. And then once we've done it in general, it would work in any future question, and we could just use that knowledge and answer any future questions. Okay, so let's now focus on solving the differential equation, looking back at this sort of general form that we have. And by the way, notice that it's actually an autonomous equation, which means that there is no t over here on the right-hand side. So we could actually find critical points at this stage of the process of solving. Before we actually solve it, we could tell a lot about the overall behavior, specifically what happens if you start above or below a critical point, whether you'll approach which of the critical points we would approach. So we can answer some of the questions at the end right now, but let's just stay on track here, focusing on solving this differential equation in general, and then we can come back and talk about those critical points and how we would answer those other parts immediately, even before solving. Okay, so it's separation of variables that will solve this because it's autonomous. So we can separate, bring all the x's over on the left side and the dt to the right hand side. So what that's going to look like is you could write 1 over a minus bx times c minus the d times x times the differential in x, and that we could write as some constant of proportionality times the differential in t. And it's here that we can now integrate both sides of this differential equation. And what we have here is something that we can use partial fractions to integrate. So if I have a question here that I'm going to solve with partial fractions, the more difficult, or if I'm going to solve by separating variables, the more difficult part is the partial fractions, the left-hand side. Of course, that's going to be very easy to integrate. So let's focus first on the left-hand side of the differential equation and do this with partial fractions. And what that means is that I'm going to break up this fraction here, the integrand, into two partial fractions. And just because both of these are different linear factors, we can get the capital A and B that we need here, these constants. They're going to be constants in the case because each of these are separate linear factors. We can find those A and B quickly by a shortcut that I call the cover-up method. So the cover-up method, what I would do is figure out what makes this denominator 0 and plug it in everywhere over here, and cover up the factor that goes to 0. And then look at what makes this denominator, just the denominator. If I want to find b, I look at only the denominator, figure out what makes the denominator 0, and then plug it in over here and just cover up the factor that goes to 0. Effectively, what I'm doing is I'm saying that it would equal these so long as each of them isn't 0. What would those a and b have to be? Algebraically. And you get the same thing if you do any of the other methods of partial fraction decomposition. This is just a quick way to do it by hand. When you have linear factors, if they're not linear factors, if there's a x squared there because you have a more complicated partial fraction, this doesn't work. And it gets a little bit more complicated if you have repeated linear factors and quadratic, irreducible factors. So only in some special case like this can we do this sort of shortcut. So what I'm trying to say is that if I want to find the a, I just solve for when that's equal to 0, and that would be a over b. And then I'm going to plug it in over here on the left-hand side everywhere that I see x, which is only in these two terms. But then this, of course, is going to go to 0. But I'll just cover it up and simplify the left-hand side. So I'm going to get 1 over this fraction. This is c minus a times d over b. And then I'm going to simplify that. So to get rid of the complex fraction. So that's what I'm going to use for a. It's going to be b over bc minus ad. Little b over bc minus ad. So how do I get the b? It's the same thing. In order to get that capital B, I'm going to solve c minus dx equal to 0, and that's going to give me x equal to d over c, right? That's going to, c over d. c over d. So if you use c over d and plug it in everywhere over here, and cover up the factor that goes to 0, which of course would be this one. So let's return again to that left-hand side. It's a minus bx and c minus dx, and we just do it again where we'll have, this time we're plugging in x is c over d. So if a minus b times c over d multiplied by c minus d c over d. And of course, I know that's 0, but in this cover-up method, I can just cross that out. So the result, this will simplify to 1 over a minus bc over d. And then I can simplify that complex fraction, and I'll have a d on top, multiplying top and bottom by d. This will be ad minus bc, which is similar to what I have there, right? These are similar. So this is my b right there. So now I have answers for this question. What are the a and the b? So I could say that this expression 1 over a minus bx c minus dx that I am going to be integrating, I am doing the algebra required for the partial fraction decomposition. What did I get for a? It is b over bc minus ad, the very top up there. b over bc minus ad. b over bc minus ad over a minus bx plus, and then the b, I can see it right there, it's d over ad over this c minus dx. Okay, a lot going on, so quick recap. A, capital A, is this constant b over bc minus ad that are given values in the original differential equation, and this capital B, this is d over AB minus BC, those values of course being parameters of the original differential equation that are all constants. And what I'm trying to do is separation of variables, which requires this partial fraction decomposition. So here's my A that I just found, little b, bc over, little b over little bc minus ad, and this b, that's right here, d over ad minus bc. Now, notice that these guys, bc minus ad and ad minus bc, they're just opposites. So basically what I could do is just factor out a negative. So that's what I've done here. What's happening is you could say that if I factor out a negative here, I could change this to bc minus ad, factoring a negative out, writing it on top. But if I could write it on top, actually, I'd rather just write it here and then get rid of the negative there. So that's what's happened. And so what I can see now is that I have taken my fraction that I needed to integrate, and I've broken it up into these two partial fractions, each of which will be easier to integrate separately using the natural log function, because the denominators are linear in x. And because I have this constant, bc minus ad, in each term, I can just write that, factor it out in front of these two fractions. So I'm just going to integrate this guy and integrate this guy separately. And so back to where I was working on the left-hand side of a differential equation and trying to integrate this thing, and I'm now going to integrate it after having broken it up into partial fractions. I have a constant here, and I have these two denominators that are linear in x, and I can integrate easily with the ln. So, I think we should probably be aware, that bc minus ad, that can't be 0. Otherwise, this whole thing fails, right? So if those original parameters were chosen in a way that gave me bc minus ad equal to 0, then we're not going to be able to solve it. So there must be some circumstance, in which there won't be a solution under those initial parameters. So we want to avoid those initial initial condition like that. So we're assuming that bc minus ad isn't equal to 0 throughout here. And actually right now is a good place to point out from the physical conditions, or the conditions of the original problem, assumptions in the original question, that chemical C is increasing through the combination of chemicals A and B. I also know, let me just go back to the original statement. I know that we're beginning with some amount of chemical A and some amount of chemical B, and they're going to decrease over time. So I know that this expression, or more generally, the expressions that I have here and here, each of these expressions are positive, right? Because they represent the amount of remaining chemical. So that A minus Bx and C minus Dx that we have, this expression here and here, from the physical nature of the problem, from the context in which this is being set up, we can assume that A minus Bx is bigger than 0 and C minus dx is bigger than 0. And that helps a little bit in the next step as I do some algebra here. When I use the natural log function, the arguments of that natural log, they're not going to be 0 or negative, right? I'm assuming that that each of these is um, greater than 0. Okay, so now the next task is to integrate this expression. Well, obviously we have a constant BC minus AD that we can factor out. So let's just write B over A minus BX. In fact, yeah, let's say it's minus and then D over C minus DX integrated with respect to X. So here we have 1 over BC minus AD. And then this guy right here, this is going to go to ln, and it's going to be, well, there's a constant b times the ln of, and because that denominator is not negative, I can just say ln of a minus bx. But then to compensate for the effect of the chain rule, there would be a times negative b, so I need to compensate for that. So I'm going to say times 1 over negative b to compensate for the chain rule. Plus, and now I'm moving to this guy. Really, it's a negative, right? D times the natural log of this c minus dx times a factor that results from the compensating for the effects of the chain rule. I'll have a negative 1 over d. So integrating this guy produces that, and integrating this guy produces that. And then, of course, there's a plus c constant of integration. I'll just deal with that later. So let's write this as 1 over bc minus ad. And then notice that the b that I have here would cancel with the b there, and the d that I have here cancels with the d that I have there. So this is the ln. In fact, there's a negative there, so maybe I'll just write that negative ln a minus bx. And then there's two negatives here. There's a negative and a negative there. So this actually turns into a plus ln c minus dx, plus the arbitrary constant of integration. Let's write this as 1 over bc minus ad. Now, those two ln's, they can be combined. So the one that has the negative gives me a expression in the denominator. So let's just write this as a single ln of c minus dx over a minus bx. Because I have that negative there, that's going to put that in the denominator. Now remember, we were solving a differential equation. In fact, that's the differential equation that we were solving. And this whole thing that we just did is basically that side of the differential equation. If you call that the left-hand side and you call that the right-hand side, the left-hand side is 1 over bc minus ad times the ln of c minus dx over a minus bx. And the right-hand side would be k times t plus some arbitrary constant. I'm going to call it c0 because I don't want to get it confused with the letter c that I have as a parameter. So that's where we are so far. Now, we had some initial conditions, and I actually want to solve for x. So what I'm actually going to solve for eventually is x here, right? So I have an expression that is the result of integrating both sides of the differential equation, but I don't really have my solution for x representing the amount of chemical C at any time. It's buried in the equation, and I have two constants here. I have a constant that came from the constant proportionality in the differential equation that actually is the kind of the rate of reaction. That's what this is. And this is a constant that comes from the integration that would be resolved by using my initial condition. So there were two given initial conditions, right? So we had given initial conditions that are ultimately boundary conditions. we had x at time 0 is 0, and we have x at some later time, let's just say, is some arbitrary value that in the specific example that we're working on was like 10, I think, but we just make it an arbitrary value for right now. So I can use this to get the C naught, and use this to find that arbitrary constant k. And then eventually I solve for x, figure out a formula for the amount of chemical C at any time. So let's get the C naught first. We have this relationship between all the values, and I'm now going to use this initial condition. Say x at 0, at time 0 is 0. So let's say using x at time 0 is 0. That is to say, we begin with 0 chemical C. So that's a pretty reasonable sort of starting place if there is no chemical C present. So on the left-hand side, I would have 1 over BC minus AD ln of C minus D times 0 over A minus B times 0, because at time 0, the x is 0. So of course, these are 0. And that would equal k times 0 plus the initial C naught, the arbitrary constant of integration. So of course, k times 0, that's also 0. So I have 1 over BC minus AD times the ln of C over A is equal to C naught. So that arbitrary constant of integration, it's this guy. Okay, it's coming along. Let's just simplify a little bit, and let's just say let m equal this BC minus AD expression, because it's going to come up a couple of times. So we could just write C naught, which is that constant of integration. That's equal to 1 over this m value times the ln of C over A, which are given parameters in the original differential equation. Okay, so now what's happened is I now have the C naught, and the next thing I want to do is figure out what is the K, and I'll need to use the another initial condition, boundary condition, a value for the compound at some later time, that x of t1 is equal to x1. I'm going to use that initial condition as well to plug in to this differential equation and solve for K. As we can see right here, we've now got the C naught. So let's rewrite this with the C naught and simplify it a little bit. I've decided that it'd be easier if we could just call this equal m. So we have 1 over m ln C minus dx over A minus bx equal to some k value times t times, let's say, 1 over m ln C over A. And right now I'm trying to figure out what is the K. So to solve for K, how about we write 1 over m ln C minus dx over A minus bx minus 1 over m ln this C over A. That would be K times T. I'm just going to subtract it over to the other side, and it's right there. All right, if my aim is to solve for the value of k, maybe one more step on the left-hand side here, we could simplify, factor out that 1 over m, right, ln of this c minus dx over a minus bx. That would be minus ln of c over a equal to k times t. I'm solving for k, but I notice that, again, I've got these two ln's here that are subtracted, so I could make it one single ln with a division, where I would be dividing by this expression. Dividing by this fraction means just use the reciprocal. So I'll write it one more step as 1 over m times the ln of, well, what would happen is you'd get a over c times this c minus dx over a minus bx. A little bit of algebra in there, and you'll come up with that. Now my purpose was to solve for k, so I'll say k is 1 over m times that t times the ln of, let's say, a over c times c minus dx over a minus bx. So we could find the value of k with any other boundary condition, with any other particular value for the compound chemical C at some later time, right? So again, we were going to use x at some time t1 equal to some value x1. So plugging it in here, we could find a particular k value for a particular given problem. It would be 1 over m times that initial, or that initially given time, right? The time at some future time when the chemical reaches some value, that's the T1. That would be times ln of A over C, all parameters of the given original differential equation, times C minus D times the x1 over A times B times the x1 being the amount of chemical C at some future time. That's the x1. So that would be the k value in general. Maybe you want to rewrite the expression for k in that way. And of course, keep in mind that m is defined as b times c minus a times d. And let's do another little recap. So there's where we were the result of solving the differential equation by separation of variables integrating both sides gave me this. And now I've gone through and used those initial conditions to find expressions for the C naught and the K in terms of those given initial conditions, and I defined this value M as BC minus AD, which all are values that are given in the original question. So maybe the last thing to do would be now to actually solve for x, to get an explicit formula for x in terms of t. And to do that, I'll go back to that expression there. So I'm going to solve for x, and I'll just leave those expressions, those variables k and c naught that I've defined. I'll just leave them like that for now. Except maybe I'll just write this as 1 over m ln c minus dx over a minus bx, and then I know k I've solved for, and c naught I've got expressions for those. I'll come back to those later. So if I'm solving for x, let's put the m on the other side. So this gives me ln of c minus dx over a minus bx is m times k times the variable t plus m times c naught. Now we could use the inverse. We can use the inverse of the ln to isolate, to try to solve for x. So we could write c minus dx over a minus bx is e to the mk times t plus m c naught. And there's some simplifying that I will do in a minute over here, but I think it's okay to leave it like it is on the right-hand side for now and keep focused on solving for x. Solving for x, I could write c minus dx is a minus bx times this e mkt plus mc naught. And try to get the x on one side, so we could do c minus dx is, let's say, a e mkt plus mc naught, that's a t, minus, this is bx, and then e, and then mk and t plus m and the c naught. And I want to bring all the terms that have x to one side, so I could write bx e mkt mc naught minus d times x is, let's say a e m k and t plus mc naught minus c. So I just brought this term to the left-hand side, and I'll bring that term over onto the right-hand side. And then I can factor out the x. And then once I've factored out x, I can divide by that expression there to isolate the x. So x would be a e m k t plus m c naught minus c over b e mkt mc naught minus d. Now I think what I could do is say, let's simplify this e to the mkt plus mc naught. Well, remember we have identified those values for the c naught and the k, and I think what I could do here, the best, I think some worthwhile simplification is mc naught. This we can write as e to the mkt and then e to the mc naught. But that mc naught, as you can see from right here, m times c naught, that's just the ln of c over a. So let's write this as e to the m times k times t e to the ln of c over a. But e to the ln of c over a, that's just c over a. So here I have e mkt times c over a. So if I go back to where I was with the explicit formula for x, that x, that's a e m k t e to the m c naught minus c over b e to the m k t e to that m c naught minus d. And I think I'll just say maybe what we'll do, we'll just say look at this guy right here. That's just c over a. Right? So let's just simplify it that way. So x is a e m k t times c over a, because that e to the m c naught works out to be e to the ln of c over a, so just c over a. So I can replace each of these with just c over a, and so x is, this will be, the a's will cancel here, so we have c e to the m k t minus c over, now I can see this is bc over a e to the m k t minus d. And that's okay, but how about we just multiply top and bottom by a to get rid of this little bit of complex fraction here. So I think I'll say my final answer, x as a function of time, is a times c e m k t minus a times c over b times c e to the m k t minus a times d. Or maybe one better, there's an AC that I could factor out at the top. So A times C e to the mk times t minus 1 over B C E M K T minus AD. So put a box around that. That's basically my formula for X, which represents the amount of chemical C over time, where we can get that M from using, that's BC minus AD, and we can get the K as 1 over MT1 ln, say A over C, times the quantity C minus dx1. That x1 being the given time, the given amount of chemical C at some later time. Right? That's divided by A minus B at times the x1. Okay, so kind of we can wrap it up here. Conclusion is that if I have a differential equation with this form that comes from this law of mass action, where you have some A minus Bx and some C minus dx as given parameters, and let's say that you have the initial amount for x is 0, and you have x at some later time equal to some later value x1, the solution is, what's that expression up there at the top, The solution has this form with m defined as bc minus a times d, which we have to check to make sure is not equal to 0, and the k, that's 1 over that m times that t1 value times the ln of, say, a divided by c times c minus d times the x1 value over a minus b times the x1 value. Okay, let's try it out. Okay, we went through that whole side quest because we're trying to solve and write the solution for the differential equation. So remember, in this particular case, this was the differential equation that we had arrived at, and it was given these boundary conditions. And now we have a general solution for any values in a differential equation with this form, and we have these other definitions for the parameters used. So in other words, in this case, this is the A, here's B, this is C, and that's D. So we could say we have A is 81, we have the B is positive 5 over 12, we have a C value of 43, and we have a D value of 7 over 12. So using that result, we could say M, that's BC minus A times D. So that would be 5 over 12 times 43 minus the A, which is 81, times the D, which is 7 over 12. Now, we could type it in the calculator and get a decimal value, but I think maybe what would be helpful here is to use Mathematica to write expressions for all of this. So in Wolfram Cloud, I could start off with, let's just define A equal to 81. And let's set B equal 5 divided by 12. Putting that semicolon at the end suppresses the output, so it just stores it. It doesn't print it individually, those individual values. So then I have C equal 43, and I've got D equal 7 over 12. And the first thing I want to compute is M, which is, let's say M it is B times C minus A times D. But this one I would like to output. So I'll hit Shift Enter, and I get negative 88 over 3 to have an exact value. But if we wanted a decimal value, we could just either you could just hit numerical value here, or I could just do n, negative 88 divided by 3. It's about negative 29.33. Okay, I'm also going to need to get the k value. And the k, well, it's given right up here, so I'll just type that in with the values that I'm given. In fact, I have also, I guess, given a t1 equal to, well, we'll have to go back and look at the original question. That's the t1, that's the x1 that I'll be using. So we also have t1 equal to 7 and x1 equal to 10 in this example. So I'll enter in t1 equal to 7, and I'll say x1, let's set that equal to 10. And now I can compute k, which I'll have that equal to 1, let's say 1 divided by, I'll do m times t1. And then multiply that by, in Mathematica I have to use log for the base e, natural log. We just use log like that. Bracket, I'm going to do the quantity a divided by c multiplied by c minus d times my x1. And then I want to divide that. I want to make sure I'm doing this right. I don't think I need these parentheses, but it just helps Let me confirm that I'm typing it in right. I need a minus b times x1 in the denominator, and all that's multiplied by the a over c. All of that's inside the ln. All of that's multiplied by 1 over. I don't think I need, well, it's not, I want to make sure that all that, both of those are in the denominator. So that looks good. So that's k, and I'll just hit Shift Enter there. I forgot to close the bracket there, so Shift Enter. And I would like a numerical value, so just say numerical value or just n for the value that I had before. So this is k. K is 1 over m times t1 times the ln of a over c multiplied by c minus dx1 over a minus bx1, and putting in all those values that I have, I get 0.00045, let's say 3 approximately. If I'm going to write the solution to the differential equation, I can see that I'm going to need this product m times k. So why don't we just take care of that? M times k, that's negative 88 over 3 times, I'll just use this approximate value, 0.000453. This is now approximate, but hopefully accurate enough. I can get really accurate here if I needed to. That's part of one reason why doing this on Mathematica could be helpful, just if you have issues with rounding. So let's do m times k. I defined k and I defined m. I should be able to get those, and I have an exact value for that, and I can get a numerical value. Negative 0.0132, let's say negative 0.013, let's say 28. Okay, so I think I have enough now. I can write my solution. X of t is the a. The a was 81, so this is 81 times the c, which is 43. It's e to the negative 0.01328 times t minus 1. This is all divided by the b times the c, so that's 5 over 12 times 43. And this is e to the negative 0.01328t, but then minus the a times the d. I'm looking right here. 81 times 7 over 12. So we could get decimal values for that, but just to check with what the computer has here, that does look right. So 81 times 43, and then I've got this 5 over 12 times 43, e to the negative 0.01328. That's what I have there. It's just minus 1 on top, but then minus the what happened to be the a value times the d value, which is that guy. So yep, that's good. This was correct. And that gets us part B, but the last two parts are pretty quick. So now that we have part B done, moving on to part C, how many grams of chemical C are present at time t equal 13 minutes? And so just to answer that part with 13 minutes, we could just go back to this function and plug in 13. And you could do that with any old calculator, but might be easy to type it in here. Basically what I want to do is just calculate the result of these values with 13 plugged in for time. So let's just say that's what x is, and we'll just plug in 13. So x would be, in general, I could use this formula, the general formula for the solution up here at the top. So x would be, let's say in the numerator, a times the c value times, now on the Wolfram Programming Lab I have to use exp for the exponential function with a bracket. So it's the exponential. I'm going to use m times k, but then I'll just use a specific value of 13. And then I'll say minus 1. So that's my numerator. And then I want to divide all of that by b times c. And I want all this in the denominator. So just make sure that's good. So b times c times the exponential raised to a power, that is the m value times the k value times a specific given value of 13 minutes, because that's of course what they're asking, 13 minutes, right? So I'm just plugging in 13. So m times k times t, and in the denominator you then say that's the power, e to that power, minus the a times the d value. And then shift enter. So I get an exact value, but I don't really want the exact value. I want a decimal value. So 17.16. So this is going to be about 17.1674. And when I check for what the computer is looking for, yes, that is it. That's exactly what it's looking for. Very accurate value there. So now the last thing is just to answer, as the reaction completes, how many grams of each chemical remain? Now, interestingly, I could do that question right after part A. I don't actually have to solve the differential equation to answer this last part, and that's because it was an autonomous equation for which we could find critical points and analyze the behavior in a phase diagram. So let me talk about what I mean there and how that's done. So if I go all the way back to the very beginning when I wrote the differential equation, right here in part A, as I wrote that differential equation, we could use that original differential equation to find critical points, answer that last part. We can just take the differential equation and we don't need the initial conditions, so we can find critical points because it's autonomous, meaning there's no t over here. We can find critical points. So set each of these equal to 0 to get critical points. So set that equal to 0. Set this factor equal to 0. So you would end up with x equal to, let's see, bring 81 over and then multiply by 12 over 5. So that's 194.4. That's one of the critical points. The other one, if I solve for x, I'm just going to move this over, multiply both sides by 12 over 7, and let's change the sign. So the x is 43. 43 times 12 over 7. 43 times 12 divided by 7 is like 73.71. So those are two critical points. So what we could do is a phase diagram that represents the vertical axis. It's the dependent variable. It's x. Right? And there are two critical points here. One at 73.71. Another one at 194.4. And assuming that we're starting off with 0x, if this is a critical point, we could test each of these intervals here. Here, we could test in here, we could test in here. So if you test something like 0, maybe we could test like 100, and then we could test 200 and see what the sign is of the differential equation. So the differential equation was k times 81 minus 5 over 12 x and 43 minus 7 over 12 x. So if you took something like 0 and plugged it in, dx dt, actually I'm going to assume that the k is positive because I have this growth in chemical C assumed in the context here, and I'm assuming both of these values are positive. So you can see right away that if you plugged in 0, you'll have dx dt is k times 81 times 43, and it's positive. So I know that it's increasing for any value less than 73. The function is going to approach 73 over time. Now we could plug in 100, so that if you actually started with more than 73 grams of chemical C, what would happen? So let's test, for example, the test point 100. So with x equal to 100, what happens to dx dt? What's the sign? This is k times, if I plug in 81 minus 5 over 12 times 100, and 43 minus 7 over 12 times 100. So this comes out to be positive, that comes out to be negative. So I can see that actually, if you actually had more than 73 grams of chemical C to start with, the function would actually decrease down from that. And I guess just to be complete, what if x was actually equal to 200? What would happen then? What's the sign of the derivative? dx dt. So as a test point of 200, we get k times. What I'm seeing now is that both of these are negative, which means overall the derivative is positive. So the function would actually be increasing if we had more than 200 grams, or sorry, if we had more than this critical point of 194. If it was more than 194, the function would actually increase. So that's an unstable critical point, and it would go over time. It would increase. But in every one of these examples, we're assuming that we start off with 0. So all I really needed to know was it was going to approach this. X was going to approach 73.7 over time. So to go back to answer this question, I can see that C is going to approach 73.7 because that's the lowest of the critical points. If you started at 0, you're going to approach that value. Once I know that the C approaches 73.7, we can now go back and plug in 73.7 for each of these factors to see how much of A and B remains, right? Because I know that this was my chemical A, the amount of chemical A, this is the amount of chemical B. So since I know this is the amount of chemical A, this is the amount of chemical B, and then I know that X is approaching that critical point, that lowest critical point is going to be the amount of chemical C that we approach as time continues. So we can just go back to the differential equation and say the amount of A, that's going to be 81 minus 5 over 12 times that 73.71 approximately, and figure out what that is. This is about 50.288. And the amount of chemical B, actually, I know that that 73 is exactly what made that 0. So we're approaching that. Technically, it's never actually equal to 0 in the mathematical model. Right? I had to kind of assume as we were going through the process that that wasn't actually 0. It never is mathematically, but in the physical process that we are modeling mathematically, that in the physical process, eventually that's measured as 0. So I know that that goes to 0, right? And you could just confirm, like obviously 43 minus 7 over 12. If I plugged in this 73.71, I don't have to type it in the calculator. I already know that's the number that makes this equal to 0. So this comes out to be 0. So I can answer that question now to say, right, so we've already computed that C is approaching 73.71. We've now determined that goes to 0, and this will approach 50.288 as the time passes. And those are indeed the values that the computer was looking for. All right, and that finished this problem. I hope this has been helpful.